Okay, and we're good to go.
Yeah, all right. So today I would like to talk about iterative acceleration techniques. In this audience, Green's functions don't need any introduction, but still let me just remind you what we're interested in. We're interested in Matsubara formalism formulated in imaginary time. We work with imaginary time Green's functions defined as time modular product of annihilation and creation operators in the Heisenberg picture. And we work with self-consistent methods, solving the DIIS equation self-consistently. Here, G is a full Green's function, G0 is a Green's function of independent electrons, and sigma is a self-energy. And of course, we use approximations for self-energy, and the approximations define the self-energy function that depends on the full Green's function. We may work with the Hartley-Fock approximation, the lowest order approximation, or we may work with correlated theories, such as GF2 that includes second order direct and exchange terms, and GW that includes an infinite number of terms like this. So the calculation is usually set up in this manner, that we start with the initial yes for the Fock matrix or for the self-energy, and then we use the Dyson equation to find G at a given Fock matrix or self-energy, and then we may evaluate the Fock matrix and self-energy given the functional form. And then we may extrapolate the set of obtained Fock matrices, self-energies, or make it dump them, and then we can solve the Dyson equation again. If we want to preserve the number of electrons that we want, we may optimize chemical potential, then we may evaluate energy, and we repeat the cycle. So this is the way how it is implemented now in the UGF2 program. And the purpose of my talk is to talk about the possibilities for extrapolation.
Oh, Pavel, can you turn the camera just a little bit that you actually can see you? So,
this one.
Yeah.
Okay.
Yeah, thanks. Now I can see you standing on the side. Thanks.
Okay. So most of the time, simple damping is used, that is defined here. The Fock matrix, the resulting Fock matrix is obtained as a mixture of the Fock matrix from the previous iteration with a constant weight alpha, and the same is done for self-energy. Damping usually leads to convergence, and it usually stabilizes iterations. But the problem with it is that it is very slow, and many iterations can be required to reach the convergence. Previously, there was some progress in the accelerated methods. Chienon implemented his version of DIIS that uses difference residuals. However, some results from that code were hard to analyze, because sometimes it behaved more slowly than damping, and it wasn't clear why. So I decided to separate the implementation of the algorithm from the problem, so to localize the issue, to figure out whether it is a problem with the code or with the algorithm. So I implemented DIIS and several other algorithms in a completely general way that does not know anything about Green's functions. So it is just a general code that operates with vector algebra, and the advantage of that is that I can test it, for example, on linear systems applications or on some other problems, just to make sure that the algorithm is correct. So I implemented DIIS, I implemented Kane, or parallel space accelerated in exact Newton method, and LCIS, or least squared commutator in the iterative subspace. I also implemented several types of residuals. The difference residual, where the differences between self-energies taken as a residual and the generalized commutative residual. If we take the Dyson equation and multiply by G from the left and from the right and take the difference, we can arrive to this commutator, which is a direct generalization of the commutator residuals commonly used in Hartree-Fock calculations, where the commutator between the density and the Fock matrix is used. Let me just go through the conventional DIIS definition, and then I will tell what the features are in the Green's function matrix. So in DIIS, we have a sequence of vectors, Vi, that converge to some target vector V star, which we interpret as a solution. We can always write the vectors Vi as a final vector V star plus the error Ei. Now, in DIIS, we seek linear extrapolation of the vectors Vi, and we can write it down given this representation. And if we want to have a sequence of extrapolated vectors that reach the convergence, we can immediately see that we must have a necessary constraint on this coefficient that they must add up to 1. And the remaining part is called an extrapolated error. And the DIIS is formulated as an optimization problem that minimizes the squared norm of this extrapolated error. How it is done? Mathematically, we use Lagrange multipliers, where we write down this squared norm as a quadratic form, depending on overlaps, and this constraint is built into the Lagrange multiplier, into the Lagrangian. And then we can take the derivative of this Lagrangian, equate it to 0, and obtain this set of equations. Now, we may have, in general, we may have complex extrapolation coefficients because the self-energies are complex that we put as vectors. But if we think a little bit about it, we have a set of inequalities associated with causality, and once we have coefficients that are not non-negative, we may violate some of these inequalities. So maybe it's better to constrain the coefficients such that they're real or maybe even positive. So, but if we say that they're real, then only the real part of this overlaps appear in the system of equations, and it seems to be very stable. And the magnitude of these coefficients can serve as some sort of diagnostic of how well the DIIS extrapolation is performed. So if the coefficients are very big, then the extrapolation is maybe not very good. Now, in LCIS, in the original formulation of LCIS done for Hartree-Fock and DFT, both the Fock matrix and the density are extrapolated with the same coefficients, and then the commutator between the extrapolated quantities is assembled, and under DIIS constraint, its norm is served as an objective function. So here we can do something very similar. We can extrapolate self-energy and the mean both Fock matrix and the dynamical self-energy and the Green's function with the same coefficients. We can compile a commutator from the extrapolated quantities, and we can put the necessary DIIS constraint on the coefficients. And we can say that, okay, this is the squared norm of this commutator is our objective function that we want to minimize under this constraint. And for this purpose, again, we can compile a Lagrangian. But here, because this objective function is a quartic function, So here, since it is not a production form, it won't lead to a linear system of equations. And we need some iterative procedure to solve it. So in the original publication, a Newton method was used, but it didn't have some sufficient details of how it is implemented. So maybe there is some freedom of how it can be implemented. So I implemented a Newton method for solving this problem with backtracking line search. And because it is a constraint optimization, I put some safeguards with the tangent gradient projection to make sure that the step does not step out of this necessary constraint. So Chem formulated it somewhat differently. So it is formulated not in terms of objective functions, but in terms of approximate Newton method. So the goal in Chem is to find the root of the vector equation, and the new vector is interpreted as a current position of a vector plus a step, and the step is found from the Newton, from just Newton method. Of course, in practice, when we don't know the exact question, we may want to approximate it, and in the subspace methods, there are ways to do that. So here, the Jacobian is approximated just considering finite differences between the subspace vectors. And this directly leads to the action of this Jacobian on the vectors that we can plug in. Ideally, we may want to use some type of preconditioning to define the action of the Jacobian on vectors. But here, preconditioning is unknown, so when we go to a subspace formulation, we can split the sequence of vectors into the space of the differences and the outside space. The action in this subspace can be obtained through this finite differences, but the action from the outside space is not really known, so we can either precondition it if we know the problem well, or if we don't know the problem well, we can just say that okay, maybe it's close to 1. And in practice, it doesn't matter that much for the problems that I looked at, because this component is very small, so the exact preconditioning is not that important. So once we plug it in, once we say that okay, this projector acting on the space of the differences is some linear combination of the space, and once we plug it in, we arrive to a set of linear equations for coefficients. Here and here, the matrix A is compiled from the differences between the vectors that we want to solve and the space of the residuals that we want to minimize to 0. And the structure of the system actually tells us something that will be apparent later, but it will be kind of hard to deal with. So we have less degrees of freedom than in DIIS. In DIIS we can choose whatever residuals we want, but here we must maintain some caution. For example, commutative residuals don't work because it will lead to an ill-defined system of equations. So let's see how it all works in practice. So this is a very simple example, probably the simplest that I can come up with. So this is just a beryllium atom. The iterations start from the 0 temperature 104 yes, and these are the GW iterations. So here on the vertical axis, I show the changes in the density matrix that are printed in the output as the DMD. And on the horizontal axis, I show the iteration number. So the temperature is pretty high, but not that high. So character of the final solution is very similar to zero temperature solution. And the dimension of the subspace is kept just by two vectors. This is the minimal subspace to make a fair comparison with Denton. So what do we see? We see that when we use the difference residuals, both DIIS and Chem lead to highly oscillatory behavior, and the quality of these iterations are really very similar to Denton. So we don't get any advantage when we use difference residuals with both DIIS and Chem. When we use commutator residuals, we have the opposite picture. Both commutator DIIS and LCIS behave very well in the beginning, but then they enter some numerical noise. So if you need a really tightly converged solution, I recommend to switch here from the iterative procedures just a simple Denton to converge it up to the numerical accuracy. So
Tell them what is the delta gamma.
yeah, it is the difference in density matrix. So it is the norm of the difference between the density matrix in the subsequent iterations, and that is printed as DMD in the output. So what happens when we increase the temperature? The difference residuals diverge. So they go bananas. I tried different ways of constraining them such that they don't diverge that much. I can say that whatever I do, I cannot outperform a simple method. So maybe the difference residuals, the difference residual choice is not the best option, but the commutator residuals behave very well and very stable. And I think the reason in this behavior is the following: that when we define an error as a difference residual, we're really biased towards self-energy. So when we use difference residuals for a quantity x, we may obtain a good approximation of x, like a good extrapolation of x, but it may not be a good approximation for 1 over x, right? And this is why the Green's function and the density matrix need to be taken. So in order to obtain a fair extrapolation for x, we must also take into account 1 over x in one way or another. So commutator residuals take it into account, and we have kind of fair gain for both self-energy and Green's function, and it seems to be pretty stable. So since many people are interested in solids here, these are some results for one of the solids that Young Bin shared with me. And so I can run whatever algorithms I have. The iteration starts from a DIIS, DB0, and then you can see an interesting picture that if you use Denton, it may lead to some illusion of convergence, right? So for example, not a very severe Denton can be used here. So first it kind of converges and then it diverges. If the Denton is more severe, it kind of again converges, but then stops converging. So maybe Denton is a little bit dangerous in this respect, that it can lead to some illusion of convergence when it is not actually a convergence. But it looks like the subspace methods with commutator residuals are very stable and very similar to each other. And I tested it on a number of solids, bismuth, vanadate, nickel oxide, a few others, and it seems to be working fairly well. There are some examples that are still challenging, and I want just to say what they are, so you can be aware of it and maybe have some ideas how to solve it. So if we go to restricted versions of the methods, then in strongly correlated systems, it's easy to end up to something poorly behaved. So this is a very simple example. This is a stretched hydrogen molecule that I tried to run with restricted G flow starting from a restricted hard-to-form gas at low temperature. And here the iterations go bananas, and it doesn't matter how severe a damping I use, so it doesn't converge. And the commutator methods also don't work if I execute it in this manner. So what can we do? So it seems to be a challenging problem, challenging convergence that limits the application of the restricted methods. It turns out that we can think about the physics of what is going on. If we go to the high temperature limit, then we can disable the correlation completely. At the high temperature limit, the Hartree-Fock method becomes exact because all the correlation is disabled. And if we keep the system to a high enough temperature, then we can effectively disable the strongly correlated part of the problem and make it weakly correlated. And then maybe we can cool it down and converge it back. And it seems to be working pretty well for a number of cases. So I tested the hydrogen molecule, all sorts of clusters with hydrogen cubes, and breaking of multiple bonds or high bond order. So this is a stretched nitrogen molecule where the triple bond is broken. Pretty strongly correlated system. So if I heat it up to a high temperature, then the restricted Hartree-Fock converges very quickly, and if I start from it, the restricted G2 also converges without any problem. Now, if I take the restricted G2 solution from it and decrease the temperature and start from it, then again, the convergence can be easily reached. And then I repeat the process, I take the final solution and reduce the temperature and run it again and again. And in this manner, one can really arrive to a very low temperature and obtain the restricted G2 solution for a strongly correlated case. So here, once the temperature decreases, the correlation becomes stronger. And in this regime, the subspace formulations indeed become superior because the subspace vectors stabilize the iteration. So here, I need at least 5 subspace vectors to make sure that all the iterations are stable. And there is no apparent winner, so here I show both CDIIS and LCIS. Sometimes one is better, sometimes another is better, so they are very comparable with each other. Okay, we have a recently published paper on that, so if you would like to know some minor theoretical details, please take a look. And now I can transition to a more practical part, where I can tell you how to run all of this stuff. So the code is available within G2 and it works for Hartree-Fock, GW, and G2. The implementation is very general, so if you implement some other method, it still will work with something else if you would like to have it. And it works both for solids and for molecules, so it is completely general. However, there are a few limitations of the implementation. I was more interested in the correctness of the implementation rather than in speed, so I didn't put NPI parallelization, but it doesn't seem to be very important because the cost of the valuation of self-energy is much larger than the cost of the evaluation of overlaps or commutators. So unless you want to run enormous number of iterations. This does not. This is not that important. At least I run pretty big systems like multi-log site with 6 by 6 by 6 grid, and I didn't really notice like this step. So that just a single digitable iteration is much more expensive than all the ones. So also it's not very clear how to implement the restart, like whether one wants to recover the whole subspace or maybe some part of it. So at the moment I have only the limited restart, right? So basically all the old functionality works, but they don't reduce the entire space. So if you want to restart the calculation, first it will build the extrapolation space and then continue working. But I will talk about like how to restart the calculation correctly. And also I have a very experimental feature which I call minor iterations, but maybe known by some other names, where the self-energy is freezed and the updates go only to the fork members, and then the self-energy is unfreezed. So from my understanding, this feature was around in the old code, but it is not yet in the new code. And I can give some comments about that too. So how to use it? I implemented it in the way such that I used the most number of keywords from the previous implementation, and both implementations are available. So DIIS code uses 3 parameters. The Chem's implementation of DIIS uses 3 parameters: DIIS size, DIIS start, and DIIS interval. So the DIIS size defines the subspace size. The DIIS start defines when to switch from Dante to DIIS, and the DIIS interval defines which iteration perform DIIS extrapolation. So my code doesn't use the DIIS interval, so it just uses the extrapolation and all the iterations, and this does not seem to be a problem with the commutator formulations at all. But it is a problem with the difference residuals that I don't recommend to use. So in order to activate my code, a user must specify a new DIIS equals true, and if one wants to use a commutator version, com_DIIS equals true should be used. It will activate the commutator residuals use. I play with trust region techniques, so basically if the extrapolation coefficients are very big, then the extrapolation may be very poor, as in the case of the difference residuals. So I put some constraints, like how big the sum of the absolute values of the coefficients can be. But may not be kind of optimal, right? So, but basically, this parameter specifies it as a default, except to some big number. So it probably doesn't matter in practical calculations. So far, if you use commutator formulation, then the coefficients are fairly small, and this is not needed at all. And here are the recommended settings. I don't recommend to go to a very big DIIS size. Usually, if you have a weakly correlated system, small subspace size works very well. Something about 3 to 4 vectors. And if you go to a very big subspace sizes, in this case, it can slow down a little bit, because it will use it will damp it a little bit too much. But if you have a strongly correlated system, then maybe going to a bigger subspace sizes is necessary, because it will stabilize the behavior of iterations. But again, it shouldn't be too much. So for nitrogen molecule, just 5 subspace vectors was enough to have a very stable convergence. and DIIS start when the iterations should start. In practice, I see that if you so it depends where you start. So if you start from the DIIS and let's say run GW, then the changes are pretty big. So maybe DIIS is not a very good starting guess for GW. So I find that it is much easier to convert GW if you start from a country guess than the changes in the fork matrix are not very big, and the conversions can be reached in fewer iterations. I usually put it 2 or 3, and it seems to be working fine. So when the start is less than the DIIS size, my code just uses the available subspace. So if it does not have enough, so if it has a number of subspace vectors less than the specified DIIS size, it will just use the available subspace vectors for extrapolation and then grow the subspace size until this limit is reached, and then grow to the whole vectors. So this is an example of an output for nickel oxide that I used recently. So everything is just as you usually use the calculations, except this part. So here I put these new parameters. Well, we can drop this one, so it's not that important. But yeah, just this is how it can be used.
Oh, well,
Yes?
you have a damping parameter in there of 0.3.
Yeah.
It will be ignored.
So not in the beginning, right? So the first iteration, like before this DIIS start, it will use damping, and then once iteration is reached number 5, then it will switch to the DIIS. So it is needed for the first iteration just to make sure they don't go bananas.
And the damping of 0.3 means that you get 0.3 of the new solution and 0.7 of the old solution.
Yes, that's correct. You can also use LCIS. You don't need to specify new DIIS or home DIIS parameters to do that. So you can just say LCIS equals true. I also look like how one can avoid this numerical noise near the convergence. So I put this parameter LCIS threshold here, so it's a switch to this direct damping-like iterations where the commutator evaluation is not used and the subspace is not used as straight iterations in the end, just to avoid this numerical noise. It seems to be fine for molecules, but in solids, honestly, I can never reach this regime where this noise appears. So in solids, I can go straight like 10 to the -7 in density matrix energy, and the noise doesn't show up. So at least in nickel oxide and in silicon. So maybe for solids it's not that important. I use some variables from DIIS, such as DIIS size, just to specify the subspace size for LCIS, and DIIS start to specify when the iterations should start. So one of the caveats of LCIS comes from the fact that it uses the commutator between the extrapolated Green's function and self-energy, and effectively it is a quartic function, right? And that's why it uses in total the number of commutators as the dimension of the Fock space to the dimension of the subspace to the fourth. So it can scale quite badly with the size of the subspace size. So I recommend to keep it reasonably small, like 2 to 4, maybe 5 if you have a nitrogen molecule, right? But don't just like DIIS is more forgiving, right? In terms of cost with the subspace size, but the LCIS is worse in terms of scaling. So keep it small. And finally, if you want to use K, you need to be aware that it can work only with the difference residuals, because the commutative residuals lead to an ill-defined set of equations, so it won't work at all. So you need just to specify K equals 2 if you would like to use it. However, in practice, I see that it behaves very similarly to the DIIS with the difference residuals. So I cannot really find the case where this external correction is very big. Theoretically, it is known that when this external space correction is negligible, then it is almost exactly as DIIS. So one of the aspects is how to restart the calculations, since the calculations are very expensive and can take some time. I can tell you what I usually do. I didn't test it very well in other regime, although it seems to be working. My implementation stores the subspace on the disk such that it is not stored in memory. So I store the vectors in DIIS, or I store on disk, or I store the residuals on disk. So in order to restart the calculation, I recommend just to remove these files. But don't remove your simulation file. And then you can specify the start equals true. Maybe you can put the DIIS start at some early stage, and then you can start the calculation. So if you are unsure which damping you want to use, you can look at the previous iterations and just steal damping as one of the extrapolation coefficients. It seems to be working. At least it can give you an idea what damping parameters should be. I also tried not to remove this, and it seems to be working, but all what I'm saying is that it is not very well tested. So, and finally, this is a highly experimental feature with micro-iteration. So what it does, first it does full update, does extrapolation, and then it does a bunch of cheap iteration where the dynamical part of self-energy is frozen and the updates come only to the Fock matrix. And I implemented only commutative DIIS for the updates of the Fock matrix, but micro iterations can use whatever else is available. It is a somewhat experimental feature, and although it seems to be correct, in practice I see that sometimes it works. So for very weakly correlated systems, it leads to fewer expensive iterations. However, when I look at something intermediately correlated or strongly correlated, what I often see is that the iterations kind of stuck. And I think the reason behind it is that if the self-energy is strong, then the gradient may point to the opposite direction of the Fock matrix, and they kind of pull each other to the opposite directions, and the result is kind of stuck in between, and the convergence is not reached. But still, if you would like to play with it, if you would like to look at it, there are two parameters how you can activate it. So you can say like how many micro iterations you want. Like you don't want like 100 micro iterations, maybe a few, just run a quick update of the Fock matrix. So for example, micro itermax equals 10, and you can also specify the commutative DIIS subspace for the micro iteration as shown here. Micro DIIS size equals to something. And that's it. I can answer any questions.
All right, thanks.